All right. So Deutsch algorithm. Okay, today we are going to see Deutsch algorithm, and definitely, like, if you have a notebook, that will be really good, because this is how I teach. So sometimes I use presentation slides, but sometimes for the algorithmic derivations, which has a lot of mathematics involved, and you need to go into the depth to understand. At that time, I use the pen tablet format. So if you have notebook, then it will be really good if you could write all these things down. But yeah, all these materials will be shared with every one of you, and even the recorded video as well. So what is Deutsch algorithm? Let us begin. So what is Deutsch algorithm? So Deutsch algorithm, if you see, it tackles a problem. Okay, this algorithm, this quantum algorithm, is one of those first algorithms where historically, if you see, this algorithm was developed by Deutsch, and that's the name of the scientist, Deutsch, and he tried to show some sort of quantum advantage. Does, like, theoretically, of course, not practically, because in those times, 1960s, 70s, 80s, we didn't had quantum computers. So theoretically, can we gain some sort of advantage compared to classical computers? So Deutsch algorithm is going to actually show that indeed we can have some sort of gain. So Deutsch algorithm tackles a specific problem. Okay, tackles this problem. So what is the problem? The problem is that given a black box, like, given an unknown function, if we have an unknown function which is implemented, let's name it as UF, okay, unitary F, let's say a subscript F, okay. If you have a black box function, so given a black box function, okay, let's name it U subscript F, okay, implementing some unknown function, remember. Okay, so this is what you have to remember. The function is unknown. Okay, in our case, we will be seeing several oracles which will be known to us just for verification purpose, but you can also implement some other kind of oracles as well, which is completely unknown, okay, which is considered as unknown. And then the algorithm will be determining whether the function is constant or balanced. So these are the two conditions. So UF implementing implementing some unknown function. What is the function f? Let's say, so we have f, and then 0 1. So f takes two values, 0 1, and it throws the output 0 1. So basically these are the inputs and the outputs. So it takes inputs in terms of 0 1 and throws output in terms of 0 1. Okay, so that is how it is. And then the question is that determine, we have to determine whether f is constant or balanced. So there are two conditions, constant or balanced. This is what we need to, this is what Deutsch algorithm will be doing, right? It will be defining, it will be seeing whether this is a constant or a balanced unknown function. Okay, so therefore first point in this will be that Deutsch algorithm illustrates key ideas of this is one of the very first algorithms which was demonstrating the key ideas of quantum parallelism. Parallelism is nothing but superposition, and quantum interference, and quantum interference that are used in all useful quantum algorithms, right? These are the techniques which are used in all useful quantum algorithms. We're already aware about this, right? The second point is it's one of the first quantum algorithms which showed quantum algorithms may be more efficient than the classical counterparts. As I mentioned before, this is one of those, this is the beginning of some, you can say this is like one of the beginning stage of quantum revolution where scientists and mathematicians, physicists were working, and computer scientists, of course, because this is computing, and they were trying to figure out an interdisciplinary field, right? Quantum computing is what? Quantum computing is an interdisciplinary field, right? It combines several disciplines, right? Computer science, engineering, mathematics, right? Physics, chemistry, etc. It combines various fields together, okay, to achieve some kind of certain objective, right? So that's why in those days they were working on interdisciplinary research and trying to find out that if theoretically can we gain something by doing this theoretical analysis. So Deutsch algorithm is output of that theoretical analysis. So it is one of the first quantum algorithms which showed quantum algorithms may be more efficient. Okay, more efficient in terms of what? In terms of time, like time complexity, space complexity, as you might be familiar, right? In computational complexity classes. So efficient in terms of that actually, then their classical counterparts. Okay, then their classical counterparts. Okay, now let us start defining the problem. What is the problem? So let us start defining the problem. So let f, as we have defined before, let f be that function which takes some binary values 0 1 as input, and it gives some binary results 0 1 as output. Okay, so let f be a binary function. Okay, f is a binary function, that means a digital function. Because remember, we were already having some a lot of maturity in the field of classical computing at that time, right? So therefore it was very obvious to have some new motivation for a computing resource which could be also very analogous to classical, which we can map the classical domain or find some sort of analogy between the classical computing domain and the new field which is called the quantum computing domain during that time. So with this there are four possibilities. Okay, so there are four possible functions f. What are those possible functions? Let us see. So we have f0, which is 0 to 0 and 1 to 0. Okay, so this is one type of function where we have 0 as input, 0 as output, 1 as input, and 1 as output. Okay, then second one we have f1, which is 0 input, 1 output, and then 1 input, 1 output. So basically the opposite of the F0, okay, where you can see that the outputs are constant, right? Okay, and this is one of the criteria, right? Constant or balance. Remember, we are about to find out whether it is a constant or a balanced function. This is the criteria of constant function, okay? Whenever we have this kind of function where the output remains constant regardless of the input provided to the quantum circuit, then that is known as constant function, okay? So let us elaborate a bit more. So if you put f of 0, this is the input, and then output equal to is output, which is 0, then f of 1 as the input, but you get 0. Similarly, f of 0 is 1 and f of 1 is 1. So what is this? This is the constant function. Okay, this is the constant function. Now let us take a look at the criteria of the balanced function, right? What will be the balanced function? F2. F2 will be 0 goes to 0. That means 0 input, 0 output, 1 input, 1 output. So now with the input, the output is also changing, as you can see. Earlier in the constant, with regardless of the inputs, the outputs are constant. Either it is 0 constant or either it is 1 constant. But here you can see, when you have 0 input, you have 0 output. When you have 1 input, you have 1 output. Similarly, the last condition, and you can already guess it, what could be the last condition, which will be the opposite of F2, that will be F3, which will be 0 gives you 1 and 1 gives you 0. So 1 input gives you 0 output and 0 input gives you 1 output. So again, in a more clear term, we have f of 0 is equal to 0 and f of 1 is equal to 1. And soon we are going to also write the XOR condition for this. Okay, next we are going to write the XOR condition. And here we have f of 1 is equal to 0, and this is what? This is balanced function. Okay, so whatever unknown function which is encoded by UF, that unitary, if it satisfy one of these four qualities, one of these four parameters, four goals, then we are able to say that whether it is a constant or a balanced. So let us note down the XOR condition. Okay, the problem is to determine if an unknown binary function f is, so the problem is to determine if an unknown binary function f, and you can see that also. Before I proceed, I would like to say that you can already see this function is a very simple version. And the reason, because why this is simple, you can ask this question: why are we considering to learn this algorithm, and why this is important? So again, the same point I would like to repeat: this is important because it serves you as a motivation to show that quantum computing does have some advantage over classical computers in terms of complexity, and that is why we use quantum computers, right? Because we need to have a better complexity, or we are able to solve hard problems which are not solvable by classical computers. So this is one of those first milestones where we show that indeed, and theoretically, of course, practically also we will see tomorrow, where theoretically we see that indeed we are able to have some quantum advantage over classical. So therefore, this binary function for constant, so this is the XOR condition. So please note it down. For the constant, you have f of 0, let's say 0 input is given, XORed with f of 1, let's say 1 input is given. If it turns out to be 0, that means if it is basically trying to say that if it turns out to be constant. Okay, this is in the XOR way of writing. Okay, that means f of 0 is equal to f of 1, right? That means the outputs are constant. Whatever you give as input, you get the same result when you change the input also. That's what we saw, right, in the table above. Whenever we were giving 0, we got 0. Whenever we gave 1, we also got 0. But again, in another case, we also saw that we got 1 as output in both the whenever both the inputs were changing. Okay, so that is what it is trying to say. Therefore, you can say that when the algorithm output is 0, it means the unknown function is constant. And for balanced, what about the XOR condition for balanced? The XOR condition for balanced will be very simple. F of 0 XORed with f of 1 is equal to 1. Okay, that means outputs are unequal. F of 0 is not equal to f of 1, and therefore whenever the algorithm output, and we are going to see what is the algorithm output later, whenever the algorithm output is 1, that means balanced it is a balanced function. Okay, with these things covered, then now we are seeing, now we are going to see the comparison between the, in very short, we are going to see the comparison between the quantum function, quantum binary function search, and the classical binary function search. Okay, so the Deutsch algorithm is a, it is a what? It is a quantum algorithm. It is a quantum algorithm capable. It is capable of determining the value. Okay, it is capable of determining the value of f0 XORed with f1. Okay, that is this is the meaning of the quantum algorithm, right? We are basically trying to find out whether it is a constant or balance. So we just showed a more shortcut method, which is this method, f0 XORed f1. So basically evaluate this result. If it comes out to be 0, that means you are constant. If it is comes out to be 1, then therefore your function is balanced. So it is a shortcut way of determining the value of f0 XORed with f1 by making, and remember, and this is the important, by making only a single query. Okay, by making only a single query to the oracle. Okay, oracle of what does it mean, single query? That means like only in one time. That means the algorithm needs to be applied only once, and you will be able to immediately find out whether it is a constant or a balance rather. But in the case of classical, there will be two evaluations. Okay, how classically? So let me write it. Classically, two queries are necessary. Okay, how two queries are necessary? How is that? Two queries, two evaluations need to be done. Okay, two evaluations of functions f for what? For input is equal to 0 and input is equal to 1. Why is that? Because remember, classical computers are sequential computers, right? How does your CPU works? You might have studied this already. CPU is central processing unit, right? And how does the CPU works? If you have done assembly language coding or any kind of coding, you already know that CPU works in a sequential fashion. Okay, especially in the assembly language, if you have done, you already know that if you have a adder, if you have a adder circuit, then definitely there is also a storage mechanism. First you need to move the numbers to the storage, then the number will be processed in the storage, and then it goes to the adder, and then another number will come again it will be stored, again it will be going to the adder, and then you will be providing the assembly language code for the operation, whether it is a plus, minus, multiplication, divide, etc. Okay, so you are doing each of that step by step, right? So first one number goes into memory, then it moves to the ALU, arithmetic and logic unit, right? Then secondly another number goes then again into memory, and then again it is moved to ALU. Then you give the operation to the ALU, right? And then that is how assembly language works, right? If you have idea, I mean, if you do not have, then please do not worry. But just to give you an example that how CPU operates, okay, CPU operates in a sequential manner, right? So that is a classical computer, right? But quantum is not that. Okay, quantum is inherently parallel. Remember, quantum is not working sequentially. Here, CPU, the manufacturing of CPU, which we do, it has several threads. Of course, it can do some sort of parallel processing, but inherently it is having a sequential operation. It is not parallel. It is not inherently parallel. We are manufacturing it. We are trying to manufacture it in a parallel way. But remember, when CPU's fabrication is done, the inherent architecture and the main notion of that is a sequential computation. Okay. Therefore, for input 0, you have to first check, and again separately input 1 you have to check. Okay. But for quantum, you don't have to do it. You can check it only in once. Why? Because of quantum parallelism. That means superposition, right? You already know that with the help of superposition criteria, you are able to manipulate several qubits or several quantum states at once, right? So because of that mechanism, this is why quantum computer is powerful, right? You do not have to manufacture a separate core mechanism for quantum. It is by nature, the quantum mechanics is by nature, the superposition is present there. You just have to utilize it. So by nature, it is a distributed computing mechanism. Okay, so this is very important to understand. That's why I emphasize this point. Okay, how this is what separates classical computers from quantum computers. But not only this, but quantum computers also have some other facilities which you are already aware about: entanglement and interference as well. So with the help of interference, certain amplitudes cancel out, and so they basically constructive and destructive, right? Certain amplitudes are moved towards higher probabilities, and certain amplitudes are moved toward lower probabilities. So therefore, what happens is that certain states will get a more boost to be found out during measurement, and other states will get diminished to be found out during measurement. Okay, that is the concept of interference, right? So superposition, interference, okay, these two are playing a lot of role in Deutsch algorithm. Okay, and that is what we named as quantum parallelism and quantum interference. So quantum parallelism is nothing but superposition. So remember, this is why, like, quantum is so powerful, because in classical you are manufacturing that sequential, but here you don't have to manufacture that. So therefore, in a black box fashion, what we can do is that we can draw this diagram. So let's say some input is given. It can be any input, and then we get, this is the notation for this output, y XOR f of x. While once we do the algorithm, once we start the analysis of the algorithm, then these things get clear. So you don't have to worry about y XOR fx. Just remember that this qubit in the end is ignored. This is not measured. Okay, just you can note it down. This is not measured in the algorithm. This qubit acts as a supporting qubit, okay, to provide quantum interference and quantum parallelism. Now let us take a look at the oracles, right? We have not taken a look at the oracles, so let us take a look at the oracles. What will be the oracles? So oracles for Deutsch algorithm. Okay, so let us take a look at the oracles. What are the various functions for which we have various oracles? So let us take a look at all those functions which we saw before: f0, f1, f2, f3, those functions. Okay, so let us take a look at that. So I am going to make a table. So functions, here we have functions. Then let's define the uh, the inputs and the function output also. Let's say fx, and let us also say the type, and then most importantly how the oracle looks. Okay, so this will be the table. Okay, let us draw this table. Then it will be giving us more clarity on, like, what kind of oracles we have. And again, of course, like, you can play and with Qiskit and craft more oracles as well, as whenever you feel. So that's always there. Okay, now f of x is equal to 0. That means always 0 regardless of the input. So regardless of 0 or 1 as input, it is going to be 0 0. Okay, and this is the constant which we saw just now. You can flip the pages of your notes and check that this is the constant which we wrote. And then what is the oracle for that? So very very simple. The oracle, what will be the oracle? So this is the oracle for that. Okay, this is the oracle. So just these states are coming, and just the same phi x or fx notation. Okay, nothing is applied. Okay, that is the oracle, right? What is the meaning of that? Nothing is applied, that means identity, right? Nothing applying means identity, correct? You have already learned in single qubits lectures, right? Previously you have attended several lectures, right? Single qubit, multi-qubit, what is a block sphere, what is a q sphere, what kind of visualizations you have, density matrix simulator, etc. You might have studied all this stuff, not density matrix, but yes, the diagram of the density matrix, of course. But yes, but you are familiar, right, that when nothing is applied, that is equivalent to applying the identity gate. So therefore this can also be represented, so I can write it, so you can also represent it like this, I, and then again in parallel I. Okay, this can also be represented like this, because applying nothing means identity. Okay, then next one will be our, so this is basically f0, okay, which we wrote before, f0. Now I am doing f1. Okay, so for f1 we were having all the outputs as 1 regardless of the input. So 0 1, and then we have 1 1. This is also constant, right? And the oracle for this is simply applying a Qiskit. Okay, simply applying a Qiskit. This is the type of oracle which we have for this type of function, and again those same things you can write. Okay, so I'm not going to write them again and again, but please note them down. And then secondly, then we have uh, f of x is equal to x. Okay, so this is f1, this is f2. Okay, f0, f1, f2, remember from the previous what we have studied just now. 0 1 0 1, right? So giving 0 input, getting the output as 0, giving 1 input, getting the output as 1. This is a balanced function we saw. Okay, and then what will be the oracle? So this is the oracle, very simple. So just apply a C not gate, that's it. Okay, these are the, and then again the same notations. Okay, and the final one, this is f2, and the final one, which is f3, is given by f of x is equal to x XORed with 1. Okay, so that means whenever you have 0 0 as input, then 1 will be the output, and whenever you have 1 as input, 0 will be the output. And this is also balanced, which we have seen before. And this is also very simple. So we have the C not gate, and we also apply a Pauli X gate as well. Okay, and rest of the notations remain the same. Okay, so these are the types of oracles, and we are also going to, of course, verify them on Qiskit as well. We are not going to leave it there. But now we have to see the steps of applying the Deutsch algorithm, right? Before we go into the circuit analysis of Deutsch algorithm. And you might have also done circuit analysis for super dense coding and quantum teleportation as well. Yeah, so it should not be something new to you, because those are also protocols, right? Super dense coding is also a protocol. Quantum teleportation is also a protocol, right? So the same kind of calculations happen in Deutsch algorithm as well. And Deutsch George, as you will see, is just a generalized version of the Deutsch algorithm. Later we are going to see that. Okay, so steps of Deutsch algorithm. Okay, what are the steps? So what are the steps of Deutsch algorithm? So first step. What is the first step? Apply apply Hadamard gates to the input state. Okay, what is the input state? Gate 0 and gate 1. Okay, I'm just ignoring the tensor for now. It is of course tensored. Okay, it cannot be like that. Okay, but just writing in a different way. Okay, but yes, you can write gate 0 tensor gate 1 as well. That means two qubits are there, right? That is what it means, two qubits. First qubit is defined in gate 0, second qubit is defined in gate 1 to to produce a product state, basically tensor product state of two superpositions. Okay, so basically we are applying the Hadamard gate and bringing it into superposition, right? I mean, this is a basic step, right? I mean, if you do not apply Hadamard gate, then what will happen? Basically you are not doing any quantum at all, right? Because why? Because you are not utilizing the property of quantum parallelism. That's why. Okay, that is how it is different, right? As I mentioned you have to make it different, right? Quantum is different from classical. How will you make it different? You have to bring it into superposition, right? And Hadamard gate does it very well. So therefore, not only Hadamard, there are other gates as well, right? Rotational gates of blocks were are also there, right? Rx, Ry, Rz, they are also there. But yeah, let us like consider for simplicity that Hadamard is there, and you apply Hadamard and produce a product superposition state. Then what will be the second step? Then second step will be apply UF. Okay, UF is the unitary, basically, which encodes your unknown function. Okay, as I have defined before, UF is that unitary to to that that product state. So now this is important to note. Okay, UF will be applied to that product state. What is the meaning of that? That state which you have, which you got after applying Hadamard to both the qubits, is a superposition, right? So therefore, this UF will be applied to that whole superposition state. That means all the qubits will get manipulated or get computed simultaneously. Okay, this is what is superposition, right? What is superposition? A linear combination of quantum states, right? So we have already created a linear combination of quantum states, and now onto that linear combination we are going to apply an oracle or of unknown function, okay, which is encoded, which we named as UF, and it will act simultaneously on all the qubits. This is an important point to remember, and this is how Deutsch algorithm is utilizing quantum parallelism property. Okay, so try to connect the concepts which you have learned before in your previous classes. This is like, you can say that this algorithm is a very good application of quantum interference and quantum superposition. Okay, so take it as an application. Okay, and try to connect the concepts together what you have learned in your previous classes. Okay, and we apply F on this state. What state? That superposition product state. Okay, on this state in, and we are going to do explicit calculation of how that is applied. Okay, we will do it one by one, but remember, all those calculations is happening internally simultaneously. Okay, but we are going to show it when we are doing calculation. We cannot do it parallelly. We are humans, we are not computers. So therefore we are going to see it, how that oracle is being applied to all the states, to that superposition product state. Okay, during mathematical analysis. Okay, so this state in terms of the unitary operator. Okay, in terms of the unitary, what? Unitary operator. What is the unitary operator? What is the definition? Uf, you already know this. Okay, x y was given as input, and you got x comma that same thing, y xor f of x on the second qubit. Okay, and then second qubit will be ignored, as you will see now in the steps. You will see, okay, third, then in the third one only apply. Okay, then what you're going to do, so after you have applied the oracle, so first you applied the superposition, right? First you have applied the Hadamard's, then you have applied the oracle, right? So HH, you applied HH Hadamard gate to both the qubits. Okay, there are only two qubits in Deutsch algorithm. And then to both of that superposition state, you applied the oracle UF. And now what you are going to do is that you are going to apply the Hadamard gate to the first qubit. Okay, so apply Hadamard gate to the first qubit, leaving the second qubit. So consider second qubit as that supporting, it is like a, remember, like, it's like, it's just like a movie, right? In a movie you have supporting characters, right? You not only have just hero heroine, but you also have some supporting characters also, right? Without supporting characters, if only hero and heroine are there, then how will the movie run, right? That doesn't make too much sense, right? You need to have several supporting characters, right? So this second qubit is your supporting character. Okay, and first qubit is your hero. Remember, you are going to take measurement of the first qubit. Okay, so this is the fourth one. Okay, that's the last step. Make a measurement on the first qubit. Okay, and already you can see we have not applied Hadamard gate, we have not touched the second qubit. Okay, in the third step itself. So make a measurement on the first qubit. Okay, make a measurement on the first qubit. So therefore, quick revision, what we did till now, what we did first of all, we applied Hadamard gates. We started, first of all, where we started with this state. Okay, where I'm going to draw the circuit, do not worry. Okay, I'm just going to revise. We started with this state, ket 0, ket 1, right? Then we applied Hadamard to both the qubits. Okay, second step. Then after applying Hadamard, we received the superposition. Okay, we received the superposition state of those, both of those qubits, 0 and 1. Okay, and then second step will be you applied the UF to that superposition state, which will be applied simultaneously to that superposition state. Why? Because of the quantum parallelism. Then third will be applying the Hadamard gate to the first qubit, not doing anything to the second qubit. Okay, we leave that second qubit, and then finally we take measurement on the first qubit. With this, now we are ready to see the quantum circuit picture. This steps gives you the algorithm. These steps, algorithm is nothing but a sequence of steps to achieve a particular task, right? So this is the algorithm. Basically, these are the sequence of steps to achieve the particular task. What is the task? The task is to find whether the unknown function UF is constant or balanced. Remember, that is the task. Okay, that is the end goal. So therefore, what will happen now? Deutsch's algorithm, quantum circuit. Okay, quantum circuit analysis. You can call it analysis, or you can call it mathematical analysis, or anything. Okay. Now, what will happen? Let us see. So let's say you start with ket 0. Okay, you have ket 0, and you start with ket 1. This is what we saw. This is what we just now saw, that you have ket 0, ket 1, and you are going to apply Hadamard gate, right? So let us do that. Okay, so apply Hadamard gate. So we applied Hadamard gate. Okay, we will be also solving this circuit tomorrow, because now it's quite a lengthy derivation. So tomorrow we are going to solve detailed mathematical analysis of this circuit. Very, very important. And also we are going to verify each of the oracles in Qiskit tomorrow. And then we are also going to see Deutsch-Jodza algorithm, how Deutsch-Jodza generalizes Deutsch algorithm. Okay, how Deutsch and Jodza is the name of another scientist. Okay, another renowned quantum scientist. Okay, so we have ket 0, ket 1. then we applied Hadamard gate, and then we apply the unknown UF. Unknown, right? UF. For us, it is known, of course, because we already studied the types of oracle. F0, F1, like how the oracles look like. It is not unknown, but actually in real life, Kate, you can consider it as unknown. Okay, let's say if someone doesn't says you what is inside the oracle, it is just like a black box to you. Okay, but from the output itself, you can say what the function was. Okay, whether was it a constant or was it a balance with the help of Deutsch algorithm. Okay, so this is the this is UF, and then we have Hadamard leaving the second qubit, and then we take, this is the fourth step, then we take what, this is the measurement, right? We take the measurement. Okay, this we take the measurement. So let us write down the ordering. So this kind of circuit analysis makes it very easy, right? You have all the steps given. So this is step 0, and this is step 1. Then you will have step 2. Okay, step 2 will be very large. Okay, step 2 and 3 calculations will be very large because Hadamard is being applied again. Okay, remember, and when nothing is applied, remember in the second qubit nothing is applied, that means it is equivalent to identity, right? Always remember this. Okay, do not forget this concept. Okay, when nothing is applied, that means it is identity. 2, then we have 3, and then this is the final step, and let us also name them. Okay, we can give them some nice names using the Greek alphabets, right? So let us take the alphabet phi. Okay, so let's say it is phi 0. Okay, let us say this is phi 1. Okay, then phi 2 and phi 3, and then this is what, this is phi 4, and phi 4 is going to tell you that where you are going to, what will be the result of your algorithm, whether it is 0 or 1, and from that you will get to know that indeed the unknown function was whether constant or balanced. So let us, since we have a few minutes more, so let us try to just write the step 0 for this circuit. So 0, as you know, in the very beginning. So let us write step 0 for this circuit. Okay, so what is step 0? So initially we prepare we prepare the state. Okay, we are going to prepare the state basically. So what will be what is the state? Phi 0, get phi 0 is equal to get 0, get 1. Okay, or you can also write it 0 1 like that, as you always write for multiple qubits. So it's the same thing. You can also include the, you can also write it in other format also, like this also you can write. It's just a shortcut way of writing. Okay, then what will be step 1? So let us do till step 1. Then from step 2, it is quite large. So we will continue it tomorrow. So step 1, what will be step 1? Apply, apply Hadamard gates to phi naught, right? To create superposition state, right? We have to create superposition state. Okay. So therefore, what will happen with get phi 1? Okay, ket, now ket phi 1. Okay, ket phi 0 we have already seen what is that, and ket phi 1 will be what? Hadamard tensor Hadamard, because there are two Hadamards, right? So therefore Hadamard tensor Hadamard applied to ket 0 1 basically. So therefore phi 1 is equal to Hadamard tensor Hadamard applied to both the qubits. ket 0 and ket 1. You can write it ket 0 1, ket 0 tensored ket 1, or you can write it like this also. Okay, there is another way of writing. You can write it like this if you are uh, if you want to be very very specific, then you can write it like this: Hadamard applied to tensor 0, Hadamard applied to ket 0, sorry, and then tensored Hadamard applied to ket 1. So you can write it like this also. So there are various mechanisms of writing, and you find out from the literature automatically once you start reading the literature, start reading various textbooks also, start exploring the field more. Then slowly you gain experience, right? And doing more tasks, doing more teaching, doing more research, you gain gradual experience over years, and then you find out these things, right? Because sometimes what happens is that not every book will mention all the notations, right? I mean, that's impossible. Not everyone can write all the notations, so therefore slowly we get to know it from the literature while carrying out analysis. Now what is going to happen? So Hadamard applied to ket 0 will be what? So ket 0 plus ket 1 divided by root 2. Okay, and then ket 0 minus ket 1 divided by root 2. Okay, right? Because Hadamard applied to ket 0 is what? Ket 0 plus ket 1 divided by root 2, right? And then, so what is this state? What is ket 0 plus 1? This is also we write as plus state, right? This is also written known as plus, and this is also known as minus, right? We say that also, right? So basically ket plus and ket minus, right? So therefore, once we take the take the multiplication, etc., so we are going to receive phi 1 is equal to what will be 1 by root 2. 1 by root 2 will get multiplied. So let us take the constant factor out. So the factor will come out as 1 by 2, and then therefore we will have ket 0 0 minus ket 0 1 plus ket 1 0 minus ket 1 1. So that is the superposition state of two qubits. Okay, where the first qubit is ket 0 and second qubit is ket 1. So I will stop here now, because the second step is quite large. It's more, we have to do a lot of calculation, and step 3 is also large, 4 is also large. So we are going to finish it tomorrow, and then after that we are also going to see the Qiskit notebook for Deutsch algorithm. We are going to verify that experimentally whether those oracles which we saw today in the class, so we saw several oracles today in the class, these oracles. So indeed, are these oracles constant or not, right? You have to verify, right? Whether these are constant or not by applying it to the Deutsch algorithm and by calculating the output, where output will be given at what? In the first qubit, right? After you are only taking measurement of the first qubits. Therefore, that is your algorithm output, right? As I mentioned you before in the very first section, algo output here. Okay, remember these small things. Okay, algo output we saw. So this is basically your first qubit result. Okay, after taking measurement of the first qubit, the result which you are getting, that is your algorithm output. Okay, and if it is 0, therefore the unknown function, the UF encoded function, is constant, and if it is 1, then it is balanced. So let us stop here, and let us continue tomorrow again in the morning, 10 to 12 p.m., 10 a.m. to 12 p.m. As you all are familiar with, the timings have not changed and they remain the same. And then again we have class timings from 7 p.m. to 9 p.m. Okay, so let us stop here and let us continue forward tomorrow. Okay, so I am going to stop the recording.